Thanks for coming to our spring Seamless Astronomy Colloquium. And I'm very, very pleased to introduce my friend and colleague, Josh Peak. And he's going to tell you about the diffuse universe and some nice science results and the kind of statistics and technology that one uses to get to them. But let me just tell you that the reason that this colloquium is a little bit special is that Josh was an undergraduate here at Harvard. I believe he worked with Dr. Reed over here, first row. I don't remember because, you know, Josh and I are the same age, so I was just in college somewhere else. But anyway, and then he went to Berkeley. And so the reason that we have these very odd snacks is because Berkeley has a tradition of having the oddest combination of snacks. So this is in Josh's honor, but he did complain that we should have red vines instead of Twizzlers. This is the West Coast equivalent of Twizzlers, so I apologize, Josh. But anyway, so Josh went after Berkeley. He was a Hubble Fellow at Columbia for a while, and he's done a lot of beautiful work on atomic hydrogen and interstellar medium and other aspects of the interstellar medium that he's going to tell you about today, including a lot of stuff about magnetic fields that he'll also tell you about in an ITC talk at 1 o'clock, I believe, where there will be pizza, not just licorice. But importantly, Josh has just recently taken up a new position at the Space Telescope Science Institute, where he is an assistant astronomer and archive scientist. But most importantly, he's essentially one of the first seriously hardcore, what we now call data scientists, who's working at Space Telescope. And Josh and I have done a lot of work in the last year that some of you have seen for the publications task force for the AAS. And so you hear Josh's mellifluous voice on the videos demonstrating the new technologies that will be incorporated in the AAS journals, but that's mostly not what he's going to talk about today. So I will sit down and let Josh talk to us about the diffuse universe. Thanks, Josh.
Thank you, Alyssa. Thanks for having me. So yes, I'm Josh Peak. I'll be talking to you today about the diffuse universe, catalogs, continua, and their combination. This is not at all just my work. This is work by Susan Clark, a graduate student that I work with at Columbia who's pursuing her thesis with me, and actually some very exciting recent work that we've just come up with in the last couple of weeks by Kirill, whose last name I'm still working on pronouncing, and so I'll show their faces with their work. I tend to talk really fast because I'm excited about this stuff, and I also have this bad habit of leaving words off my slides. Which is a terrible combination. So what I've done is, if you get lost, you can always just look up at the top of the screen, and that will be basically everything you need to know about what I'm saying. You can even just not listen to me at all and read that, and you'll be okay, I promise. Okay, let's move forward. So astronomy has always been this science of catalogs. I think as astronomers, we take this for granted. This is going to be my earliest reference from Ptolemy. And what you're seeing here is just a catalog of stars and different constellations, their brightnesses and positions on the sky. And the reason we're able to do this is that the sky is black, right? We have this beautiful black sky, and then I don't know, these points of light. And those points of light really lend themselves to cataloging very easily. And I'll show you sort of what modern things you can do with this. The obvious thing you can do is make a Cartesian plane and plot x versus y. This is an interactive data visualization. I'm showing you a movie of it, but you can click on it yourself and play with it, of the moons of Jupiter. So these are taking the different moons of Jupiter and plotting their different positions across from each other and being able to select them. And this works because a lot of the mass around Jupiter is in its moons, not in some complicated diffuse interacting field. And so you can make a list of them, you can select them, you can go back and forth between them, and you can gain knowledge. So sort of my favorite point here is that it took many centuries to get from the first Galilean moons to the next moons, and that's just because there's a differential in mass of a factor of 10,000, and you can just see that by looking at a plot very, very easily. So this cataloging is critical to our understanding. But this is kind of paradoxical, because what we know now is that the universe is mostly diffuse. You've got this big chunk of dark energy, and then you've got this also huge chunk of dark matter. Now, dark energy is extremely diffuse. It's even like conceptually diffuse. We don't know really what it is or means. And then dark matter, we've gotten to this idea of halos of dark matter, but we know that things are more complicated than that. It's not just a list of individual dark matter halos. And then even when you get down to the atoms, most of the atoms are in plasma and gas. They're not inside of things that we can easily make lists of. Okay, so basically what this talk is going to try to do is reconcile these two problems. The fact that a lot of what's interesting in the universe is diffuse, and yet most of our tools are based along catalogs. And to further complicate this problem, objects in the universe that we're interested in studying, say galaxies, are not related to their diffuse components in any kind of simple way. So here, this is adapted from Berhouzi et al. This is the mass of galaxies, log space in stellar masses, and this is the amount of baryons available to them. And what you see is that if you had a bunch of baryons for a given halo, some galaxies down here are really good at keeping their star, turning those baryons into stars, and some are bad, really bad, and some are kind of mediocre. So there's not an obvious relationship. When you have this diffuse material, you can't just say, well, there's a galaxy, and so it has this much gas associated with it, and just sort of think of it as some kind of simple thing. The relationship can be very complex and confusing. Okay, so if we're going to use catalogs, if what we have in life are these objects, how are we going to get at the diffuse material? So this is a classic. One way to get at it is to look at absence. Right now, here what I'm showing you is a globule that's being obscured by that is obscuring background stars, and so you can tell there's obviously something there. In fact, whenever I look at the night sky, from say the southern hemisphere or somewhere dark, and you see these dust clouds, I always think, well, isn't it obvious that those were clouds and not holes? But maybe that's something I've learned, and it's just you can't unlearn it. In any case, this is true for dust. It's also true, for instance, say quasar absorption lines. Right, we can study the intervening material by looking at absence in the catalog. There's a little bit of light missing from a quasar. So same concept. The continuum is harder. This is kind of an ugly image of the whole sky in H1. And what you see is that in neutral hydrogen in our galaxy, it's everywhere. Everywhere you look, there is stuff. The sky really is not black. And so it's very hard to take something like this and use the emission that's coming from these hydrogen atoms and learn something about individual objects. Now, as we move through in velocity space here, and I'm just stepping through in velocity space, you start to see these little structures that are peeking up off the top of the galaxy. And these things are the high velocity clouds. And I argue that the reason that people initially studied the high velocity clouds so much is that you could study them. You can look at that black sky, and you can draw a circle around that cloud, and you can say that's a cloud, and I can give it a name. Okay, and so the ability to name things is really what motivated our ability to study them, right? The rest of the galaxy is this very complicated intermishmash. It's very hard to tell what's what, and there's many people here in this room that try to do that. But when you look at the high velocity sky, you're actually able to break these things out into individual clouds, give them names, figure out their velocity, and use that to trace things like galaxy formation. These are neutral clouds floating around our galaxy. They're somehow related to the rate at which our galaxies are creating gas. They're related to star formation. So this is one way of taking a continuum, all of this material that's everywhere that's emitting, and extracting a catalog from it and then using that catalog to learn something. So this is another mechanism to go from the diffuse universe to a cataloged universe. Now, what we learned from the CMB is that the unsegmented continuum can be a really powerful tool. So what this isn't is an image from the South Pole Telescope of the CMB. What this is an image of the South Pole from the South Pole Telescope where we've got the CMB. You do a Fourier transform. You scramble the phases, randomly assign the phases in Fourier space, and Fourier transform back. And in fact, I've done that 10 times. And you can see they all look, roughly speaking, the same. And what we learned very early on is that when you want to look at these background fluctuations from the cosmic microwave background, you really don't want to think about it in this space. Nobody goes and looks at the CMB. Very few people go and look at the CMB and say, oh, well, there's a cloud, and I'm going to call that C, and this one's B, and look, they're next to each other. That's not useful. You think about this in terms of the power spectrum. And people have tried to do this in the modern universe as well. So in the modern universe, right, you have gravity. This is the same thing, except what I've done is taken images from the neutral hydrogen sky and applied the same game. The last one is the real image, and you'll see that it doesn't look a whole lot the same. And in fact, looks really, really different. There's a huge amount of information in phase space, and we can't just throw away the information by looking at some kind of power spectrum. Lots going on in terms of the phase domain. Okay, so different ways to try to get at information from this diffuse universe. And when you go to the modern universe, when you go to redshift 0, you can no longer use these tools that say the universe is a Gaussian random field and all the information is in the power spectrum. Okay, so structure of the talk. First, how do we use catalogs to inform our understanding of the diffuse universe? Let's start from the catalogs we have and try through absence to understand what's going on in the diffuse universe. Number two, how can we interpret the continuous universe, this emission data, in the modern universe when you can't just rely on something like a power spectrum, when you need tools that can interpret phase? And then finally, is there a way to combine these data? To put these two kinds of data sets together to learn something in hybrid. And this is a lot of the stuff I'm going to be talking about at the very end of the talk happened last week. So this will be hopefully exciting, and hopefully you'll have some feedback for me. So catalogs, continua, combination. Catalogs. Okay, so as I said, there's these two ways to study intervening gas, either through dust or through lines. This is a nice, some nice work by Vergely in 2011 and Rosine Lalleman's group. And what you see here is a bunch of stars in the galaxy. There's the sun, and this is just 100 parsecs. So we're just looking at a little slice of the galactic plane. And you can look at these stars either in terms of how reddened they are, or in terms of how much absorption they're getting from a particular line, in this case of sodium-1. What I'm showing here is that they trace each other very nicely in this context, where in the galaxy, spectral lines and dust often trace each other, depending on which lines you choose, of course. So I'm going to talk mostly about dust today, because I want to use big data sets, and there are lots of big data sets where you can actually get photometric information. And this will be a theme throughout the talk. So just a brief commentary on dust, just to get us all on the same page of what I'm talking about. This is a great slide from Leah Corrales at MIT. And this is her periodic table of dust. And indeed, basically most of the metals that you see in the sun, these are what they're made up of, right? Carbon, nitrogen, oxygen, neon, etc. And aside from nitrogen and neon, many of them depleted into dust grains. So a lot of the metals that are coming from stars are actually on grains of dust. And this is actually really important. If you want to understand how stars form, how galaxies form, you want to understand sort of their exhaust. And their exhaust is in metals, and those metals are all in dust. So by studying dust, you're actually getting at interesting questions of star formation and galaxy formation. Also, it has this obscuring property that some people love and some people hate. I go both ways. But in this case, what you can see is that the amount of extinction, the amount of light that is scattered out of the line of sight, is more on the blue side than on the red side. So here we are in the infrared, here we are in the ultraviolet, and what you see is there's this reddening curve. So essentially, when you look at an object that's behind a bunch of dust, it tends to look a bunch redder. And so we use that reddening as a tool for understanding where that dust is, and therefore where the gas is in the galaxy, or anywhere. Okay. So this is the service part of the talk, where I try to help everybody else. I'll tell you what I mean here. So this is work by Schlegel, Friedman, and Davis, you may have heard of. This is the best dust map, it was at the time, may still be, the best dust map of the sky. And what you're seeing here is the galactic plane, and then the galactic zenith and galactic anti-zenith towards the South Pole. And while most of the dust, of course, when you're looking at it, is in the plane of the galaxy, the part that's actually most important at some level, in terms of understanding where it is actually above the plane. And that's because that's where we do our deep cosmology, right? If you want to go look at some objects that are far away from the galaxy, and you want to understand what they actually look like, you need to subtract this effect off. And so our precision in this high part of the sky, I'm showing you here the footprint of the Sloan Digital Sky Survey, main galaxy survey, that area of sky is critical to do right. And the way we do these maps is we see far infrared emission from the grains. We've got these dust grains. They're embedded in radiation field. They absorb the light. They re-radiate it. And you see this sort of map of the sky. And that'll tell us where this extinction and reddening is happening. But there are problems. There are problems with these maps. And even though these maps are very good, people have shown that there's a real issue. Now, this is a really confusing diagram. I'll walk you through it one piece at a time. So this diagram is based on some known errors in the dust map. We'll talk about those known errors later. But it's to assume that there are some errors in the dust map that we know about. Now, take some subset of galaxies that you're going to use to do some kind of large-scale structure cosmology experiment. So maybe your galaxy is at a redshift 0.7 or at 2. You can think of your favorite experiment, and you're doing some kind of optical survey. And now what you want is to have your bias be small, right? You don't want to have errors in your data. Basically, if you integrate for long enough, after a while, you just reach your bias limit. And what this is saying is that for known errors in the dust map, you run into biases in a measurement of, say, non-Gaussianity, or a measurement of the change in W with time, which is to say measurements of how lambda is changing with time, dark energy, once you go to these kinds of galaxies for this level of precision, which is to say that you want your precision, you want your bias to be significantly less than your errors. So the point that I'm getting at here is that you essentially cannot do cosmology in the optical with dust maps that aren't accurate, because there's no reason to do them. There's no reason to integrate any longer, because you're completely dominated by systematics that come from dust. And don't trust me, trust these guys. Okay. So to combat this idea, we came up with this concept. To combat this problem, we came up with this concept. You've heard of standard candles. I did not come up with that concept. You've probably heard of standard rulers, things who have a known size, but when you observe them, they have a different angular size, so you can figure out a distance. We came up with this idea of standard crayons. The idea is that you know that this thing should be a color, But when you observe it in some other color, you know that there's some reddening in front of it. So this is a way to measure dust along the line of sight. So the first thing we did this with were these quiescent galaxies. So this is the Sloan main galaxy sample. This is 700,000 galaxies or so. And we plot them in this H alpha versus oxygen 2 diagram. So this is a diagnostic of star formation, right? If you have any of these lines in your spectrum, you know that there's something going on in that galaxy. We select the really boring galaxies. Now, I think of them as boring. I love them because they are boring and they all look like this. Giant piles of, K and M and G stars, nothing too exciting. When you take these galaxies, they tend to have a very narrow color locus, and I'll show you what I mean by that. I'm going to use this little Crayon logo for these. So when you see this logo, that's what I'm talking about, these galaxies. These things have an extremely narrow color locus. I'm showing you a log distribution of the G minus R color of these galaxies, and you can see the distribution we're talking about here is 24 millimagnitudes. Okay, so once you basically take out a K correction, a change with redshift, and since we have spectroscopy of all these galaxies, we know their redshifts very precisely, you see that the width of this distribution is extremely narrow. And that allows us to measure changes of dust along the line of sight. We look at these galaxies, and if they look a little bit too red in one particular direction, we know that there's dust in front of them that we haven't calibrated. And that's what this is. These are corrections to the Schlegel-Finkbeiner-Davis 1998 reddening map. This is galactic zenith. This is the footprint of the Sloan Digital Sky Survey, and you can see there are many, many areas where there are errors in the SFD map at 3 millimags. The 1 sigma error here is 1 millimagnitude, really, really small. And people in this building have improved on this work and done other really exciting things that I'm not going to have time to talk about. But you've got the idea that we're actually able to now get a proof text to figure out whether these dust reddening maps are right. We can probe the gas between us and these galaxies just by looking at the galaxies themselves. Okay, so I just want to make a little pitch about H1. It used to be back in the day, the way we did these extinction maps was by using neutral hydrogen, because neutral hydrogen was a great tracer. Its emission was a great tracer of extinction, and so that's how it was done before. So this is what you get for Schlegel-Finkbeiner-Davis using the far infrared emission from the dust. This is what you get when you use H1 from the Leiden Argentina Bond Survey, and this is what I call the truth. This is the actual color of galaxies, and they look totally identical. But when you take their differences, you find something kind of interesting. So this is the difference that I just showed you in color in the last slide, and this is the difference using H1. So this is basically the errors in an H1 map of dust. These are the errors in the Schlegel-Finkbeiner-Davis map. And what's interesting is, A, the scale of the errors is quite similar, and B, the errors don't look the same. They're not the same part of the sky. And what that tells you is combining them gives you a better map. And what we showed is that when you take these two together, if you take an FIR map and an H1 map, and you put them together, you can actually get a better answer, a better map, than just by using one or the other. And what's interesting is that the errors significantly cancel. It's not just that the errors are random, it's actually that the errors are pointing in opposite directions. And so that gives us a really nice handle. So what I'm hoping is that when we have these really awesome high-resolution H1 surveys that are going to come from these future telescopes, we'll be able to combine the H1 data with the far infrared data and make the best possible dust maps. Okay, so that's the end of the service part of the show, where I try to help the community to build better dust maps to do cosmology, and instead use dust to do cosmology directly. Okay, so dust is actually important outside our galaxy as well. This is work by Menard and Fukugita, referencing some older work by Menard et al. In 2010. And what you're seeing here is, on the x-axis redshift, and the y-axis omega dust. So you're used to omega matter, omega lambda, omega whatever, but you're probably not used to the energy density of dust in the universe, and that's what this is. And you can see it's not really big. This is 1/1,000,000th, so it's not super large. But what's amazing is that what's been shown is that there's as much dust in magnesium-2 absorbers along the line of sight to quasars as there is in just the halos of galaxies, I'll talk about this more in a minute, as there is in the disks of galaxies. When you think about dust, you think about it in the disk of a galaxy. You look at these beautiful images, there's all this glowing dust coming from the disk of the galaxy with the gas. But what we're finding is that there's actually just as much dust in the halos of galaxies, beyond the disks of the galaxies. So we can study this dust with the same tool, with these standard crayons. So instead of looking at a region of sky, adding up all of these standard crayons and saying what color is that part of sky and how different is that from what we expect, we can instead say, let's look at these background galaxies and pair them up with foreground galaxies. So when you've got a background galaxy, one of these crayons, and then one of these galaxies, you can look at them in pairs and ask, if this galaxy is in front of this other galaxy, does this thing become redder? So I have this background galaxy whose color I know, this foreground galaxy that I know a lot about, And when this one goes in front of this one, does this thing become redder? And that gives you a measurement of the amount of dust around this galaxy in the front. What's cool about this is that this foreground galaxy I'm talking about, we know a lot about, right? We have a spectrum of this galaxy. We have an image of this galaxy. We know the mass of this galaxy. We know the specific star formation rate of this galaxy. So instead of just asking how much dust is there around a galaxy, we want to know, is there more dust around big galaxies, around little galaxies, around star-forming galaxies, around red and dead galaxies? So we're able to actually break this up and ask questions about how the process of galaxy formation relates to the presence of dust around galaxies. So what we found in this analysis was that indeed we see reddening. I'm showing this in U minus G reddening, but you can show it in many others. This is the results from previous work towards quasars, and what we see is this excess of reddening inside about 150 kiloparsecs. So within, roughly speaking, a virial radius, we see this nice excess of reddening of background objects. If you just add up everything inside here, just think of this as one number we're trying to measure, you find something I think really, really interesting, which is that if you break up these groups, if you look at just the big galaxies or just the small galaxies, or just the red galaxies or just the blue galaxies, what you find is that for red and blue, not much change. So that's telling you that there's the same amount of dust basically around star-forming, whatever they call it, star-forming main sequence galaxies, red and dead galaxies, same amount of dust. So that's to say that these things, that dust lives a long time out there, right? It lives at least longer than the transition time between these two phases. But what's really interesting is that you do see a change between big galaxies and small galaxies. Big galaxies, 10 times as big, have about twice as much dust. So what that's saying is that dust does not just linearly scale with the size of the galaxy. You make the galaxy 10 times as big, you don't get 10 times as much dust around it. You get maybe twice as much dust. So you can think of this as an equation, the relationship between the mass of the galaxy and the mass of dust. And let me just put this in context for you, thinking about all the metals ever produced by a galaxy. This is a nice figure from Molly Peoples' work that I've adapted. This is the mass of galaxies on the x-axis, and then the y-axis is all the metals they've ever produced. Okay, so I'm a galaxy, I have some history of star formation, these stars have produced metals, they've released them into the interstellar medium. Where are they now? Okay, so this is where are they now. Only 20 or 30% of the metals that have ever been produced by a galaxy sit inside it. And you can see, if you look at small galaxies like the LMC, or big galaxies like the Milky Way, basically stays the same. There's this missing metals problem. Most of the metals are somewhere else. What recent work has shown from Tumlinson et al. And others is that there's a significant amount in this circumgalactic medium in the gas. These are in things like oxygen-6 absorbers, magnesium-2 absorbers, and so forth. You see this quite a bit in this warm and cool gas phase, but really only on the small side, right? You don't actually see that there's much more of it when you go to bigger galaxies. And the same thing is true of dust. What's interesting here is that it means that we're actually kind of completing this missing metals problem. We're finding the metals, most of them, on the small end. But we're not finding all of them, we're really not finding all of them towards L-star galaxies. So maybe they're in some hot flow, maybe they're in some other phase we're not probing yet. But I think this is kind of interesting when you think about it in comparison to observations of galaxies. We know that L-star galaxies are really much more efficient at maintaining their material, right? So you've got this big reservoir of baryons, and maybe 20% of those baryons turn into stars in your big sort of Milky Way-like galaxies. And the argument has often been, well, these galaxies can hold onto their material really well, but small galaxies have low potentials and they just blow the material really far away. Well, it's sort of weird, right? Because if they're blowing the material really far away, why is it that they're only blowing it inside their little halo, right? I'm saying this is all within 150 kiloparsecs. This is all near a galaxy. So what's going on that these galaxies are able to get rid of all of their material from their disk to not form stars, but still maintain all of the metals that we think they have? I don't know the answer to this question, just posing it. Okay, so this era of industrial precision photometry that's allowed us to do these studies of the extinction in our galaxy and understand where the dust is, and furthermore to understand dust around other galaxies is marching ever forward. It started with SDSS, pan-stars. A lot of great work has been done by Greg and Eddie and many other people to use pan-stars to do this kind of thing, but soon we'll have things like LSST, and then to do this at high redshift, you can even use things like W first. So this process is marching ever forward. Okay, so that's what I wanted to say about catalogs, using background objects to probe the gas in between. Let's talk about continua. And this is going to be work essentially entirely by my student, Susan Clark, who's crackerjack. I'm moving fast enough. Okay. I told you, I get very excited. Okay, so I said the diffuse universe is full of this shape information, right? You can't just look at the cosmic microwave background. You can look at the cosmic microwave background and just run a Fourier transform and learn a lot. And indeed, as far as we know, the CMB is a Gaussian random field, and there's no reason to expect that looking at phase space is going to be very powerful. Mnemonic, phase, and shape are anagrams. Okay, so the shape information in the interstellar medium is critical. We really need to get at that shape information if we want to understand what's going on. So I showed you this video at the beginning. This is data from the Galp H1 survey, which I started during my thesis. This is 2,000 hours of Arecibo data. You're looking at between deck of -1 and 38. That's the galactic plane. And we're just slewing across. And what you see is it's extremely complex. The interstellar medium has all sorts of very complicated features that do not look like a Gaussian random field. Thank you very much. And they have all of these long, slender, complicated things that we saw early on. In about 2005, we saw these long, fibrous, winding features of these guys. And we couldn't figure out what they were. They were very confusing, and we wanted to try to understand them in some kind of statistical way. But publishing this as a paper and saying, boy, don't there look like there are a lot of long, stringy things in here? Turns out you can't get that past the referee. And you need to actually say something about what's going on inside of this image. And I could just let this play forever and look at it, but I should probably finish the talk instead. Okay. Right, this was all taken with the Arecibo 305-meter largest telescope in the world. And what made this possible is two things. One is the addition of this alpha instrument. This instrument has 7 beams instead of 1. We've got the whole idea of pixels. So there's 1 pixel, we got lots of pixels, so that's cool. Thank you, optical people. No, but this is an amazing instrument where we can actually survey the sky at 7 times the efficiency we could before. And this is an instrument called GalSpect, which was made by the late great Jeff Mock, and allowed us to just turn on when other people took data. So actually, all the data I showed you, we weren't pointing the telescope. There's another group pointing the telescope, and we just flick the switch, turn this thing on, ask them to run a little calibration script, and we were good to go. So by that mechanism, we were able to gather 10,000 hours of data on the sky, which is 2 operational years of Arecibo time. Okay, so we collected all of this data together, and when we did it, we saw, well, we didn't see this. This is what you would have seen if you had used the state-of-the-art survey at the time, the lab survey. And you can see there's sort of maybe there's like a line here, or there's a thing here, but this has a resolution of 36 arc minutes. It's not high enough resolution to get at the sub-features that are going on inside of these structures. If you look at the same image, but you look at it at high resolution using the Galp H1 survey, it really pops out. You see these long, stringy things that are crossing, that are parallel. We called them fibers. And we decided we wanted to figure out what they were. And what was interesting about these fibers, it's sort of the same image but in black and white, is that they seem to correlate with magnetic fields. When you look at starlight polarization measures, these little red lines, if you squint, you might convince yourself that they're sort of pointing in the same direction as these features. And, maybe sometimes they are, sometimes they're not. And again, maybe they are, sometimes they're not. I don't know, it's not a title for a paper. So you want to do something statistical. So we developed this thing called the rolling Hopf transform. You start with this image of the sky, say. And the first thing you do is you smooth it. You remove that smoothing to create what's called an unsharp mask. So these are all sort of standard machine vision, computer vision techniques, image processing techniques. You take that image and you threshold to create a bit mask. So now I've just got 1s and 0s. And I've gotten rid of the low frequency Fourier components. You can think of it that way. Then we extract a disk of diameter dw around each point in the image. So for each point, x0, y0, we extract some disk of size dw, and we pull it out over here. And then to this, we apply what's called the Hopf transform. I'm not going to explain the Hopf transform in much detail. It's a very standard thing from the 50s. But basically what you do is, as a function of angle around the center point, you ask how many pixels are lit. So there's no pixels lit this way, and then, there's some pixels lit, so we get some power. And you get basically power as a function of angle. Okay, so as you turn around, you get lots of power, a little bit of power, lots of power, a little bit of power. Then we set some threshold, and this final purple thing is we call the result of the rolling Hopf transform, and it's basically angular power as a function of position. So you've got an x0, you've got a y0, and there's power as a function of angle. So for every image I give you, for every image I give it, it gives me a data cube back, where the third dimension is angle. Okay? And I'm going to show you a lot of times where I've actually taken that cube and I've compressed it again, because it's very hard to look at a 3-dimensional object. Okay, so now what we have is the ability to measure this correlation between this And this is this back projection. So you can see it really nicely pulls out these long, slender features. Okay. And what we find is that there's a bunch of free parameters in this analysis, but it really doesn't matter what you set as long as you retrieve something that looks vaguely like what you're looking for. So now what we do is we take every single one of these stars, we look for a small area around that star, we take the rolling Hopf transform power at that position, and we ask how much is it oriented along the direction of the starlight polarization versus perpendicular to the direction of the starlight polarization. Okay? So I'm going to show you an image where this is, they line up, and this is, they are perpendicular. The polarization, which measures the magnetic field, and the orientation of the RHT, which just measures the H1. They're aligned really, really nicely, about a factor of 8 to 1. So what you see is that in this region of the sky, these linear features correlate gorgeously with the starlight polarization. We can look over a much larger area of sky. This is the Galactic All-Sky Survey. This is the southern sky. It's many, many more stars, but lower resolution. We can do the exact same thing. What you find is that the correlation is there. You still see the correlation, but it's not scale-free. Okay? So this is to say the interstellar medium has some mechanism by which it orients the neutral gas with the magnetic fields, but it doesn't do it on every scale in the same way. It's not happening both in large scale and small scale at the same time. It's happening much more as you go to higher and higher resolution.
That was larger scale.
This is larger scale. This is the gas survey at 15 arc-minute resolution. I'll talk a lot more about this stuff in my talk in an hour, God help me. And if you're really interested in magnetic fields in the interstellar medium, I suggest you come to that talk. Because this is just really trying to give you one key piece of information. Shape information informs the nonlinear universe. If you want to understand what's going on in the modern world, particularly in the diffuse universe, you have to get at shape. This is some images from the Palomar Cosmic Web Imager, where we're starting to actually get the first images of the cosmic web. Okay? And it'll be great. You know, the first thing we're going to do with the cosmic web is ask, how much is there? That's 0th order. And then people are going to start to do two correlation functions, and then they're going to be lost, because nobody has any tools to take in these kinds of pieces of information and understand really what's going on. You know, are they flows? Are they inflows? Are they outflows? Are they connecting things? How does it work? And this is also true even when you're trying to study dark energy. So here, this is a simulated weak lensing convergence map. Okay, you can think of this as just the density of the dark matter in the universe. Let's just leave it at that for now, in a slab. This is the same thing once I've scrambled the phases, my favorite trick, right? So people want to apply the tools of the CMB to this data, even though it doesn't look like the result when you just keep the power. Okay, the tools of the CMB only keep the power, and yet this doesn't look like that. So we're trying to build some new tools. Zoltan Hyman has already shown that counting the peaks is actually very powerful, along with a number of other people, of course. We're trying to ask questions like, can you actually see the cosmic web in these images by applying linear shapefinders? Okay, so this is the seamless astronomy colloquium, and we'll come back to that point. Shape exploration is anything but seamless. Let me walk you through my life for the last 10 years. So first we had these really ratty images, and we overlaid these starlight polarization things, and we said, okay, cool, these look related, we're going to follow our nose, how are we going to do this? Okay, so then I wrote some code, I wish I had some images for this, this is a ridiculous piece of code, where I, it's like, okay, what I'll do is go in by hand, and I'll click on all of them, and then I'll make these little lines, and then those lines will go into, and that didn't work very well. I got distracted with writing my thesis. Then, as Blakesley will tell you, we convened this image processing analysis and machine vision reading group across campuses to talk about how to do this kind of work in general. And this is where I was like, oh, I know, I'll use this, what is this called? This is called robust edge finding something something. Doesn't work. Totally doesn't work at all, but it's a tool that exists in the literature, so I have some slides for that as well. And then finally stumbled upon Hopf transform, that's what this is, and then finally came up with, okay, I can use this rolling Hopf transform, we can make this work, I could do this. So this is not a seamless process, right? This is a horrible process. And if every time you wanted to discover something as interesting as this, it took a decade, we would be in trouble. So how do we bridge this gap? How do we make this process more seamless? So the short answer is, I have no idea. The slightly longer answer is, I think one thing that would be very useful is to use some of the tools that exist already that are very standard in the machine vision and and computer vision communities, OpenCV and Scikit-Image, and import them into some of the tools that we already have. I'm using my favorite local tools here, but I think this should be true for all of our tools that we use to look at images. I think you should be able to easily apply an unsharp mask to an image. That shouldn't have to be some code that you bring up. That should be a menu item. Right? There's a lot of things that are very standard image processing tools that could be very, very useful for us, not just in terms of trying to make our image most accurately represent the data on the sky, but rather to process it and learn something new from it. So I think this is something that could be useful. And then in the long term, come help us figure it out. We're throwing this conference at Space Telescope, and the basic idea is the universe is very complex. Our tools that observe that universe are also complex, and then our simulations of what the universe should look like are complex, and how are we going to relate these things together? How do we simulate the universe, observe that simulated universe, and then what tools do we use to compare that observed simulated universe with the real observations, and how should that loop work? So a lot of different people, from observations, from simulations, from theory, from big data. So if this sort of thing you're interested in, I definitely want to talk to you about it, because I don't know the answer, and I don't want to spend another decade the next time I need to do something like this. Okay. Catalogs, continua, and now we're going to talk about combining them. How do you put together the information that's coming from the continuous universe, the emission, with this extinction that we're talking about from individual sources? And this is where Kirill comes in, and it's going to do something amazing. Okay, so this is a terrible argument, in my opinion. I sold you a load of bunk when I told you that this is a good argument for the diffuse universe. I don't think of every 1,000 astronomers, 683 should be studying dark energy, and 268 should be studying dark matter, although I think there are people who disagree with me, but in any case, certainly 2 of them shouldn't be studying everything you've ever looked at with your eyes. This is not a good reason to study the diffuse universe. This is a good reason to study the diffuse universe. X-axis here is decade. Thank you, Alberto. Y-axis here is the percent time that star and formation together are in, I think, the abstract of a paper, divided by the number of times just star is mentioned. Okay, so this number has to be less than 1. And what you see is that over time, we're interested in this concept, formation. We really want to know where we or things came from. We're no longer interested in just how many things are out there and where are they. We want to get at the question of formation. So how do we get at the question of formation? Formation requires segmented kinetic information. So I'm going to go back to my high velocity clouds. These clouds, we can say they have names, right? Here's complex WE, here is complex C. They're in a place, okay? And then we need to know how far away they are. So here's some distance information. We've got this complex C, and we look at some absorption to background objects, and now we know how far away it is. So now we have a velocity, and we have a distance. Here, I'm just going to show you a cute little video. This is inside of our paper, where you can actually look and see where all the high velocity clouds are. It's amazing how far away the Magellanic Stream is and how big it is compared to everything else. But in any case, there's complex C there. So we know its distance and we know its velocity, and from that we can get at this key question: how does the material fall onto the galaxy? So we've built a small model, but all you need to know is the distance and the velocity. And between those two things, you can get an accretion rate. Well, the accretion rate is telling you something like how the galaxy is forming, and that's what we want to know. We want to know about formation. Here I'm showing the accretion rate from just neutral and low ionization high velocity clouds is actually quite low. This is nowhere near the star formation rate of the galaxy, no matter how you slice it. So we need to figure out other things about how formation in the galaxy works. I'll just show you a couple other examples. This question is a super open question to me. How does the material attach onto the plane of a galaxy? If a galaxy forms stars, does material flow in through the outer edge in some kind of big warping spiral arms that are accreting onto the galaxy? Or does it happen really at the center, where material flows up, percolates on the surface of the disk? The hot material just cools right onto the surface. So I call this the in or on problem. I want to hold a conference called in or on and put people in categories and on categories. Because there are great theories for both of these ideas. Material accretes onto the edge of the galaxy and flows through the plane, or material accretes onto the surface of the galaxy through some kind of hot-cold interface. If you knew where this material was and how fast it was flowing, you could get at this question. Because if the material was accreting from the outside, well, the stars form in the middle. If the material accretes from the outside, then it has to flow through the disk. You could actually see where that flow was happening, you could get at this problem. Same thing's true of molecular clouds or spiral arms, right? You want to know how fast material is flowing into a spiral arm. You need to know if the stuff that's moving away from you is closer to you, or if the stuff that's moving away from you is far from you. If the stuff that's moving away from you is far from you, then the thing you're talking about is losing material. If the stuff that is moving away from you is near to you, well, then that thing is gaining material. So just knowing the distance or just knowing the velocity is not enough. You need to know how the components are related, how things at certain distances are related to things at certain velocities. So there's these ideas that molecular clouds are formed by colliding flows. Just a pretty image of molecular clouds, okay, in a spiral galaxy. So everything I've been talking about is just this. This is the continuity equation. And all the continuity equation is saying is that if you want to know the rate of change of density at a position, you need to know both the distribution of material and its velocity. So this is the continuum I'm talking about, where you can get at the idea of the velocity of the gas. And this is the catalog, right? This is going to get us where the gas is in 3 space. And so I'm calling this idea of combining these things together kinetic tomography. Instead of just tomography where you're finding where all this stuff is, now you get at that 4th dimension, where you can actually see flows and you can see how things form. So hopefully I've motivated why you would want to have a 4-dimensional map of our galaxy in gas. Okay. So tomography will use reddening along the line of sight. I've showed you this before. You've got this distribution of material. You've got these stars. By looking at the stars and how well they're extincted, you can figure out where the material is. But that requires you to know distance. And there's been some great work done in these austere halls on this exact topic. So I'm going to show you a bunch of slides you've probably seen before. But in any case, if you just have photometric information, so you've got a star and you know it's got this brightness and this brightness and this brightness and this brightness and these different bands, you know that it's probably some kind of main sequence star or some kind of giant star with some amount of reddening. Okay, so that's what I'm showing you here. Here's a color diagram, and here's maybe where the star was originally, and here's some reddening vector, sort of arbitrarily drawn. You can invert the problem, and that's what Greg and others have done, is that you take these, so you take an individual star with some UGRIZ color, let's say, and you can then figure out where it might exist in a Bayesian sense in the extinction reddening space versus distance. So this is some distance, and this is sub-extinction. And so by combining all of these things together, you can actually get, on a given line of sight where you have many stars, how much extinction there is as a function of distance. So, no extinction, no extinction, no extinction, lots. And they fit a model to this. Okay. So this is how you can do this totally with photometric data. And this gives this beautiful 3-dimensional map of the galaxy. But we want to get at not just the 3-dimensional map, but the 4-dimensional map. So the 3-dimensional map, I think, is already published. It's already published. It's close to published. In any case, it's being refereed. So you'll have a much prettier diagram than the one I just showed very soon. But you've got to remember that we're entering this incredible age of tomography machines. Right? You've got pan stars with 8 by 10 to the 8 stars. But no parallax information, so you have to use this trick of knowing that stars get dimmer as they get far away. Then you've got Gaia, fewer stars but extraordinary parallax, and also some really nice ability to look at individual absorption features in the diffuse interstellar bands. And then LSFT with 140 times 10 to the 8 stars, and also some parallax information. And now, soon, later, you've got the idea that we're going to have a lot of tomography information to combine with the gas information we already have, and are getting more of. Okay, but as I said, you need to be able to associate this, right? It's not enough to say there's a near cloud, there's a far cloud, there's a red-shifted cloud, there's a blue-shifted cloud. You need to know which is which. That's the problem I'm going to try to solve right now, and that Kirill has been helping me with. So here what you have is looking along galactic longitude towards the outer galaxy. There's some carbon monoxide. This is various molecular clouds. And then this is where the extinction is, okay, as a function of distance. And you can see that, maybe certain things match up. This one and this one, they might be related to each other, but it's very hard to tell. You can't just by eye say, well, each one goes with, this one goes with that one. So how are we going to solve this problem? Well, I'm going to invoke a professor you may know, Howard Georgi. Howard Georgi is the first person to tell me that if you can't solve a problem, solve an easier problem. And that's what I'm going to try to do here. So here's the easier problem. Instead of taking these 2 maps and trying to combine them and getting an answer and not knowing if that answer is true, I'm going to start by making up a fake map and seeing if I can recover it. So let me tell you what I'm going to do. I'm going to take some data cube that has real data in it, and I'm going to extract from it an image. Okay, so this is one of my, in my case, actually H1 cubes. So I just take an image from the H1 sky to give me some sense of what clouds might look like, right? Because I don't want to just put it in a blob. I then multiply that by some distance and some velocity, which I randomly give to it. So I say this cloud is at this distance and it's at this velocity with some width in distance space and some width in velocity space. Okay, so I've got this cloud and it's at a particular distance and a particular velocity over some range of distance and velocity. Fine. Now I do that a dozen times, 20 times, whatever, and I mash them all together into one four-dimensional cube. So I'm now asking you to think in 4 dimensions, but think about how much gas there is at a particular position on the sky, right ascension, declination, distance, and then also velocity. So it's a 4-dimensional cube. So now I take this 4-dimensional cube and I project it out into what we would see on the sky from our radio observations, say, right ascension, declination, and velocity, and then what we would see on the sky from our tomographic information, right ascension, declination, and distance. So these are the things that we actually have access to, trying to reconstruct that, okay? So I've taken a fake cube where I know the answer, I project it down to the real data, and then the question I'm presenting is, can we reconstruct that 4-dimensional cube? Can we get back to reality from only these 2 pieces of information? Okay. So I'm going to use this thing called sparse non-negative matrix factorization, which I'm not going to explain in gory detail, but I want to give you the brief outline of it because it really brings together kind of the whole talk. So you're basically trying to solve this problem. Let me show you what it is. These are the data that went in. These are the 2 data cubes. The red one is the extinction data cube, and the blue one is the velocity data cube. So it's a distance data cube and a velocity data cube, and I've just stapled them together, like with a rivet gun or something. And then what I'm trying to do is decompose it into 2 components. Basically, I want there to be k clouds, where k is not too many. So I want there to be k clouds. And basically, each cloud is just a combination of an image, and that n is the image of the cloud. So n is the number of pixels on the sky. So I'm just showing you matrix math here. N is the number of pixels on the sky. So there's k images multiplied by k vectors. And each vector is just what does the distance look like and what does the velocity look like. Okay? So it's basically that I should be able to reconstruct this by a linear sum of k images with these k vectors associated with them. These are called feature vectors in machine learning land if you're a machine learning person. And all sparse non-negative matrix factorization is doing is imposing that these things are positive, and this is why you don't use PCA, right? In principal component analysis, things can be negative, so we're forcing everything to be positive because there's no negative flux from clouds. Clouds do not have negative densities, so this makes a lot of sense. And then we also enforce sparsity. This is sort of a deep concept that we want there to not be too many clouds or have too much flux everywhere. So we basically try to make this vector sparse. Try to focus all the information into a few different places. So either it's at one distance or it's at another distance. It's not at all the distances. And this works great when you've got these 2 3-dimensional domains that are nicely separated, right? This looks really nice. So what you have is this is the input ground truth, that cloud and that cloud, at this range of velocities and this range of distances, and this cloud at this range of velocity and this range of distances. And this is what SMNF gives you back, and it's a bit the same. It's exactly identical. It does a really good job in this case. Because there aren't that many clouds. When you go to 18 clouds, here's what the input looks like. Again, randomly assigned. I've just randomly given it velocities and distances and random clouds. This is totally fake made up data, and this is what it gives you back. It crushes them all into 10 clouds, and they're a mess, right? You would never believe that this cloud is at this distance and at this distance. Right? The cloud is at one distance. It's at one position, basically. So this is total failure. This is what failure looks like, where you're completely incapable of finding the clouds back and what material they have. So here's the secret sauce. The secret sauce is moving to a true 4-dimensional space. And let me explain to you what I mean. You're adding this new thing called P, which is a projection vector. And all P is telling you that I think is really important is just how the 2-dimensional space, so this is the velocity channels times the distance bands. So this is now, instead of saying, I've just got a vector that I'm interested in, that each cloud has some particular distance and some particular velocity. Now I'm saying, think of that nice little distance velocity image. It sits in that space, and this is the space that is sparse. You basically you force that space is the sparse space, and that's critical because the whole point of this talk, the whole thing from the very beginning is we lived in this sparse universe, black sky, individual points, okay? And that makes it very easy to do science. And in some sense, that's what science is, that you can describe the universe by a very small number of terms, okay? And what I'm saying here is that the interstellar medium is not sparse when you look in just position velocity or position distance, but it is sparse in the 4-dimensional space. So this sparsity is actually getting at the point that the universe is sparse, that there are a few terms that actually describe everything we want to learn. And just to show you that it works, this is the input, and this is the output. As you can see, it's mostly doing a good job. There are places where it fails, but out of the box, it does a surprisingly good job at reconstructing both the shape of the clouds and their positions and their distances. And just to show this how this looks in 4 dimensions, very hard to look at 4-dimensional data cubes. So here I'm using glue. I'm importing these 2 cubes, the true cube and the false cube, and I've just put them next to each other in distance space. So when you look at this in image space, right ascension by declination, you can scrub around, and I'm just showing you how complex this cube is, right? This cube just has lots and lots and lots of overlapping clouds in it in this space. But if you rotate it so that you're looking at a single right ascension and a single declination, and now looking at this position velocity, this is the input, and here is the output. So I'm just showing them side by side. And you can see how well at any given right ascension and declination you're recovering the distance velocity space, where the cloud is in distance and velocity. That's the input, and that's the output. Okay, that's probably enough. So, to sum up, standard crayons, this powerful new tool for the precision study of dust, which is crucial for cosmology. And there's this huge amount of dust around galaxies, which is accounting for much of the metals that small galaxies produce. We developed this new method to measure the galactic magnetic field orientation, and the shape information in the diffuse universe can be used to measure these underpinning physical processes. If you take anything away from the talk, this is just a critical thing I want you to understand. It's not just weather out there. Looking at the shapes gives you a lot of information if you have the right tools. How you make those tools, don't do it the way I did it. It took too long. To answer questions of formation, you want to get at not only where it is, but also how it moves, and associating those two things together. You've got to somehow staple them together. And this high-dimensional, sparse, non-negative matrix factorization, kinetic tomography, may be a window into this new 4-dimensional world. And I will leave it there. Thank you.
Are those fibers unresolved?
Many of them are, yeah.
The ones that aren't, what's their aspect ratio on their side?
So there's a bunch of discussion of this in the paper. It's a little hard to say. Our tool isn't really good at finding them and categorizing them, and that's something we'd love to do better at, and we actually have a student working on that this summer. Like, how do you say, well, this is a fiber and it has this length? I think of the interstellar medium as like having fibrosity, right? But it is true that it would be interesting to talk about that. There's cold neutral medium features, so they have line widths of a few kilometers per second, but they can be 10 degrees long. They can be longer than that. They're huge.
And how wide?
Many of them are unresolved.
Yeah.
We should say 4 arc minutes is our resolution. So yeah, we don't really understand how to do statistics on the ensemble of fibers. Basically, how to turn them into an object that we can then do what I was talking about on, right? They're hard to catalog. But we have elements of our group who are very excited about cataloging them, so hopefully we'll do it.
So you showed us a lot about how basically we're getting a lot of images that are not sparse and not Gaussian random fields either. And so how much do we have to learn from, Fourier power spectrum, say, is not always a very useful thing in and of itself, but there's surely many other statistics that you can compute. And how much do we have to learn from computer vision type people or other fields where they may have been working with data sets like these a lot more than astronomers have?
Yeah, there's this great set of papers I've been reading on testing the strength of fabrics. So you've got a fabric, and you have an image of the fabric, and you want to know, is this a strong fabric or a weak fabric without actually tearing it to bits? And so you can actually look at all the interconnected literal fibers of plant material, and then run a bunch of analyses and figure that out, and sort of progress in that way. So there's a sense in which vision meets learning there, where you say, take a bunch of images, I build some enormous feature space, and then I use that feature space to learn with some training set and do that. And so we are interested in pursuing that. It's an uphill battle because machine vision is a very fast-moving field. A lot of people doing a lot of different stuff, and then also not all of it is a lot of it's proprietary, so it's a little hard to sort through. But it is a struggle I'm finding. I do think that's the way to go about it.
Have you found any fields where, the particular problem of, 4-dimensional, even, say, 6-dimensional full phase information, where people have data sets that they have? Presumably...
So there's this thing called hyperspectral imaging, which is, or remote sensing it's sometimes called, and they think about this space. They don't often... They at least go to 3 dimensions, and their 3 dimensions are sort of similar to ours, and so we've been talking to them about some cool things you can do with manifold learning, where you can actually deal with slight variations from the kind of strict, it's at a distance, it's at a velocity, there's no velocity gradient kind of stuff. You can learn on that space a bit. So we have talked a little bit to the remote sensing communities. But I'm not sure there's anybody who's actually done truly 4, 5, 6, 10-dimensional stuff in this domain, because they're often working with images or hyperspectral images.
Are there, talk about sort of linear features, but how about sort of characterizing bubbles and volumes and things like that?
Yeah, that's something I'm really interested in. There are a couple of bubble finders out there that exist. And I have talked to, the Hub Transform is a tool that you can adapt to that kind of problem. I think there are other things you could find. This was sort of okay, I'm being hit in the face with this amazing information that's very clearly telling me something. And so we went and sort of traced that. Actually, in the talk I'm giving in, God help me, an hour, I'll show sort of the original work where people, Carlisle, saw these bubbles and said, oh wow, there are bubbles here, and how that informed theory immediately. So I think bubbles are a great sort of next thing to try to pursue.
I think that's an interesting point, because Josh is talking kind of about machine vision and machine learning slightly separately from that. So in other words, Chris Beaumont wrote this really nice paper about taking the output of the Milky Way project, looking at bubbles, as an input to a machine learning algorithm, right? And there the bubbles were identified by humans. It's a lot easier to identify straight lines in a machine vision challenge sense than it is to identify bubbles. And even when Chris looked at how the experts agree with each other for the bubbles, there's a tremendous amount of disagreement. And the same is true in the brain imaging community, where they're trying to find neurons, and you can make an exact parallel between bubble finding and outlining neurons and slices of brain images. And they have the same problem that you're not exactly sure what you're looking for. So when you're looking for straight lines, it's a lot easier now than other things. And so my question to you, Josh, was going to be, when you get to the actual machine learning piece, what do we do then? Do we have to get smarter? Do we have to leave people in the loop?
Part of it may be that we need to have conversations between theorists and observers, and sort of back to this mocking the universe idea, where you say, well, let's build mocks where we understand what the ground truth is, we understand what magnetic field we injected, or what supernova feedback we injected. Then we put it through the whole process, and then we can make these kinds of parallels. But then you have to use these tools on our side that are powerful, and we can sort of figure out where the errors are. But there, you have a ground truth,
Right.
And it's, I think, a general problem with the interstellar medium is that we're not at a point where things are well described.
Right.
Things are extremely complex,
So basically, you have to know what you're looking for.
which is hard,
Yeah.
as you and I both know.
Yes, we do. Let's have maybe one more question, but of course there's another thing in here, and so we have to get out and let them reset up the tables, and some of that thing is Josh in the chat. So one more pressing question, or we can just... Okay, why don't we adjourn, and then you can return in less than an hour and hear Josh talk more about magnetic field and chat.